Okay, shall we start? Okay, Assalamualaikum warahmatullahi wabarakatuh. Um, all right. So last week I did not have any class with you because I received another slide presentation from the previous lecture. So I'm consolidating the slide to give the best for you because there are different presentation of slides and try to combine them and then present to you. Right, so we have a new, I already put a new file for you. So if you go for your class work, you go to your shared folder, drive folder, those. Okay, right, so there is a new file, that is drive one, the one that I replaced a new file, okay. So we have this track one, and then for today's video, I'm going to post a video for today's lecture afterwards, and there will be a drive two, a new slide for you, and then on the you go for the simulation folder. I also shared with you the installer of Psim, the simulation package, and Psim. So those who have yet to have this PC installed in your PC, in your laptop, then you can download this setup file, then install in your laptop, right? Then we have this DC Moto separately excited file. I also shared with you the file to simulate the DC motor operation with a separately excited connection, right? And because it's very good to have this simulation because you can see actually what is happening. Yeah? When you try to learn on the DC drive, it is best for you to use the simulation package. There are actually many software or many simulation software that can do this simulate the detailed simulation. And I found if we have a MATLAB Simulink, probably some of you are familiar with MATLAB Simulink. And can I ask how many of you have used this PC?
Dah guna sudah.
Ada yang pernah guna?
Benar-benar. Psim
dalam lab
Masuk
saya.
selepas.
power electronic. Power
Betul.
electronic. Okay, great. Dengan siapa tu? Alif?
Dr. Haida.
Dr. Farah Haida, Dr. Haida. Okay. Amir dengan siapa?
Sama, saya
Yeah.
satu kelas dengan ni, Alif.
Okay. So most of you probably have experience to use a PC, so that is good. So you can also use that PC to simulate, to look at the performance, the operation of a DC motor. So last semester probably you only focus on the converter, the operation of the converter, how the current, how the voltage of any converter, and from that simulation you can predict and you can actually compare with your theory, isn't it? So it's best for you to use simulation. So and in our EPO 640 electric drive, the CO2, the course outcome number 3, is actually dealing with the PC, with the simulation. And you need to use the simulation package, IT tools to be able for you to understand the operation of the motor. Okay, so probably I want to share that. And before I go for that DC drive simulation, so this short class will be focusing on the simulation of DC motor using PSIM, and then afterward I'm going to share with you the video. Okay? And of course, you need to watch it through Add Puzzle to get the full video. Watch and counted for the attendance. Okay, so EPO 640, this is the new file that I shared with you. This is same, and then I put some extra additional notes here. DC motor introduction, then some fundamentals and how the DC motor works, and it is always based on the Lorentz force. Okay, so the Lorentz force saying that when a wire carrying an electric current is placed in a magnetic field, each of the moving charges which comprise the current experiences the Lorentz force. And if you how to determine the Lorentz force by using this left hand rule, or you can also use the right hand rule using the palm, the fingers, and everything. Okay? So you can use that to determine the direction of the force. Okay, next. And in order for you to keep the DC or the force the unidirectional, which means this converter, this conductor will experience uh, upward force, upward force, upward force, and this conductor will experience downward force. Okay, so we use this slip ring. We use this commutator, and therefore you have that unidirectional force for the motor. And then the construction of the motor, you can read again, and this is very similar to electrical machines that you did in semester 4. And then motor construction, again some additional uh, details on that construction. And then we have this operation. And DC motor, the starter poles are supplied by a DC citation IF, isn't it? Citation current IF, which produces a DC magnetic field. The rotor is supplied by DC current through the brushes commutated across the interaction of the magnetic field. There are two magnetic field and also the rotor. Rotor current also generates a field and creates the force for the motor. And we have three connections separately excited or shunt motors. This is interchange. Sometimes it's separately excited. If you have separately excited, which means both DC voltage for the motor is completely separate, different source. But if you have a shunt motor, they still have the same DC supply, but then the field windings and the armature windings are connected in shunt connection, parallel connection. Then we have series motor and compound motors. Compound motors is actually the combination of series and shunt motors. So most of the examples that we had is on the separately excited shunt motors. Okay? And we have this is the basic connection, right? Separately excited. So it comes with two circuits. So in the simulation package in Psim, you also will see two different circuits here. All right, to represent. There is a one module, they call it a module package. And that package will show you the back EMF and the field winding, right? And you can, therefore you can connect it as a separate excited, or you want to make it as a series motor, you can do it in the simulation. I will show you later on, right? So this is separately excited DC motor. And then we have this shunt connected DC motor. So we have only single source here. So this is shunt motor. Compared to separately excited, we have a different source, isn't it? Different source, and that will power the DC motor here. Okay, and then we go series motor, and then this is some applications of shunt motors. Look at that, blower fans, pumps. For series motor, we have electric trains. Some basic theories, torque equals to K flux, KT. This is the basic equation. So you have a machine constant multiplied by the flux, the field winding that produce the flux, and then the armature current. So this armature current that multiplied by flux, multiplied by the machine constant, that will give you the torque of the machine. The torque. Okay. And then we have, we look into the first separately excited or shunt motor, as I mentioned just now. We start with the separately excited, so it's just to understand the fundamental of what is the speed control of this motor. So it's best to use more convenient to discuss on separately excited motor, and then you can apply the same understanding to the series motor. So for the separately excited motor, For sharp motor, you're going to have these key important equation, right? 1 and 2 here. They are the same equation. They come from the you just replace that TD with the previous equation just now. Then you get this two equation, right? And this two equation determines how you're going to control the speed, isn't it? So this is the speed of your motor. So we have looked into the no load speed, right? This is when your load equals to 0. Huh? Your TD equals to 0. There is no, there is no developed torque. Right? There is no developed torque, and this is where the omega naught, and it represents only Vt divided by K flux. Okay, so this is on the previous video. So again and again, I hope you can rewatch it. The video always in my YouTube channel. Okay? I think you can go to. I hope you can. You already go to went to my channel and look at under DC under electric drive. Okay, there's all the videos that I've shared with you through Add Puzzle is actually on my YouTube channel, so you can watch again anytime you want. Right, and so by this having this equation, then we know that the speed can be controlled by the first one will be armature resistance. Okay, and then you can control using the armature voltage here Vt, or you can control by means of the field voltage here or field flux here. So this is the three uh, parameter that can affect or can change or can vary the speed of your motor. Okay, so we have looked into the first one, which is the armature resistance in armature circuit, whereby you just add the armature resistance, and in that, okay, this is controlling speed by adding resistance. So when we try to look into the armature, adding the resistance to the armature circuit, we always consider a constant torque. This is when you have a constant torque. This torque axis, correct? So when you have this a straight line here, or parallel line, the parallel to y-axis, parallel to y-axis, this is when torque is constant. Okay. Torque is constant. It has only one value of torque. It has only one value of torque. This is torque constant. This is the case we have a torque constant. Okay, so when you change the RAD, the additional resistance, then the speed drops from the first position here. So if you add number 1, your speed drop to R2, and R2 drop, and finally drop at 0 speed here. Yeah? R4 is when you have torque at certain value, and we have omega naught equals to 0. This particular omega 4. Okay, so and we also discuss the same this example, and this time I also put this solution with you, right? So you can download again the slide, and now we have the solution with you. We can redo it again, look at the solution. And then next we look into the adjusting armature voltage. Right. So in that case also we have the same similar equation here, and with that equation we analyze with the same torque constant, a constant torque operation. We have only one value of torque, and then we vary the V2, V3, V1, V2, V3, and as we increase the value of V2, as this is V1, V2, as we reduce, the voltage, the speed also drop, isn't it? As we reduce the voltage, the speed also drop from omega 1 to omega 2, omega 3, omega 4. Right? Okay, so therefore, this operation can be, this is the basic of speed control. Later on, we're going to look at how to integrate the power electronics, the converter, into the circuit so that you can control this VP. Okay? The idea is to control the VP. Why? Because the armature resistance control is not efficient. It's not really efficient to use the armature resistance control because it will create actually a heating to the motor. You can only use the armature resistance control for a short time, only for a short time, right? They use the RA. If not, if you want to control gain, it's not that efficient because you need to have it represent the loss. I squared R represent the loss to the motor. Okay, so therefore, the most common technique to control the motor is by using VP, change the VP, as well as to change the flux. Right, this is two common methods to control your speed of your motor. All right. So before we go, so the video that I'm going to share with you later on will focus on the converter that will change or will vary the VT here. Okay. All right. So now I'm going to share with you how to look at the simulation of this circuit, the converters, the DC motor we separately cited. We're going to look at how to simulate the circuit with a separately excited connection, and then we're going to look at if we reduce the VT, what is that will affect the speed of the motor. Okay, so now let's look at if you go to your, I can go to your, okay, this is your folder. Under simulation, there is already file DC motor here, Psim file, but that is actually created using Psim 9. I have a correct version, Psim 9. Now we're going to look at how to do that in Psim 11, 11.15. Install it. Those who have yet to have this Psim 11, you can use this setup installer file there and then try to set up or try to simulate. Okay, so we start with a blank document. So normally what you have here, look at the, okay, let's look at this circuit, right? So we want to simulate this separately excited. So we have VT, two voltage source, sorry, two voltage source, and then we have this machine, right? DC machine, and the rest is going to put in scope, some oscilloscope in the DC. Okay, so we start with elements. So I hope those who are familiar, you can teach your friends how to use a PC. Those who have yet to use a PC, please do so because it's very above. I have used so many simulation package, PC. You have the MATLAB Simulink. Also use a microcap. I also use a Saber, right, during my studies. So above all, PC is the most it's simple to use. It's a user friendly, and if you compare with the MATLAB Simulink, there are many parameters that you need to change, isn't it? In MATLAB Simulink, but in PC, the first, I mean, it always consider a default value. A default value, I mean, the simple circuit with the ideal circuit. The ideal circuits and it's simple to use. Okay, so for PC, we start with the adding the DC motor. So where is the DC motor? Go to the element, go to power. There is a motor drive module. There's a motor drive module. Look for DC machine. So there are a few motor. You have the squirrel cage. This is induction machine, right? Later on, we're going to use induction machine. So there's a few module here. We have a DC machine, a brushless DC machine, synchronous machine, a switch reluctant machine, a more advanced switch reluctant. We're going to learn how on the switch reluctant later on. As well as the brushless DC machine. So we start with the basic DC machine. Right? So click DC machine, and we have that. Okay. So this is to represent what we're going to do, have. This is to represent the armature circuit, and this will represent the field winding. The field winding. So if you double click that, there's okay. So there's a parameter that you need to supply for the module. The armature resistance 0.5. And we have this armature. This is a default value. You can change it. Change in terms of what is the specification is given to you. So this is a default value. It's already there. 0.5, and we have this armature inductance 0.01, which is 10 millihenry, and then we have this 75 ohms. Remember, your field windings is always higher, a lot higher than the armature resistance. So RF is normally 100 compared ohms, and this armature resistance is below that one. Sorry, below that one or 1 point something. That is the standard value of armature and field winding resistance. Okay, then we have this LF 0.02, moment of inertia J, and we have the rated of this DC machine is correct. It's 120 volt DC, and the rated current is only 10 amps, and the maximum or the rated amp when it operates with 10 and 130 ohms. So you get this base. We call this as a base. What's a base speed? This is the base speed, and this is the current, IF current, and therefore you have the rest. Okay. So if you divide 120 volt to 75, you get that 1.6. 120 volt divided by 75, the field winding resistance, then you get 1.6. So that's IF. Okay. So you don't need to change anything on that. Then you put in what? The source. You have two sources here. Therefore, go to elements again, go to power, and then sources, voltage, and DC sources. We have two sources here. One, two there. Right, so let's change that to VT, and this is 120 volt. Right, there you go. Then we have this as a VF, and this is also 120. Right, and this you can put to look at RA. Important to have RA and RF. The rated speed. Okay, so next is to look into the load. Okay, this is a DC motor source. Now we're going to put in the load. So if you look at my slides just now, we have a constant load, isn't it? We discuss on the additional resistance, and when we look into the armature resistance, we always look at the constant load operation, isn't it? The constant load operation. So here, we're going to choose, go to elements, go to power, and there is a mechanical loads and sensors. Right? So I go to that mechanical load sensors and look for mechanical load with constant torque. There are a few selections that you need to have. One is a mechanical load of constant torque. You also have a constant power. So when we talk about constant power, this is the operation beyond. When we want to operate beyond the rated voltage. Remember, we can increase and reduce the voltage, the terminal or the armature voltage, isn't it? But we also have this motor which has its own rated, the maximum rating of the motor. So we can actually increase the voltage up to the maximum rating voltage of the motor. So if you want to increase more the speed, you will no longer can use the armature voltage control. You have to change to the field control. You have to change to reduce the field winding so that you're going to increase further the speed, right? And in that operation, when you have the motor at maximum voltage, rated voltage, and you reduce the flux. Remember, we have Vt over K flux. So if you reduce the flux, that is known as a field weakening operation. Okay? In that operation, we are actually operate with a constant power load. Okay? So there are a few here. So that is just to explain on what is a constant power, what is constant torque. Right? So, so that's why you have constant power. So if you want to work under the flux weakening control, then you need to use the constant power load. But in this case, we still under voltage control, armature voltage control, then use the constant torque. Okay, so click that, then there you are. So if you double click that, it will give you nothing. It's a constant torque, one, and moment of inertia. This is the ideal case. Ideal case. So it's constant torque of one and moment of inertia of zero. So leave it as that. You can put that right. Okay. So now we're almost done. Then we need to what? To have the sensor to look at the speed of the motor. So where is this sensor? Go to the elements again. Go to the power. Under the same mechanical load and sensor, then you have these sensors. There are a few sensors that you can choose. It can be speed sensor or torque sensor. So now we are more interested in look into the speed sensor. So you just click that speed sensor. That okay. Then you just connect all of that. Okay. Okay. And wait, we have yet to complete because we need some probe, isn't it? Some scope, oscilloscope. When you do this, as you simulate, and then you need to watch the monitor the voltage or current across each element here. So first, we're going to use the probe voltage probe. So this is the voltage across of the elements there. So we have this is VT, right? And this is VF. Okay, what else? We want to look at the current. So I have to disconnect that. Use a current probe. Okay, use a current probe as well as the other probe here. Is okay. Then connect all the So this is IA. This is IF. And double click the speed here. For the gain one, okay. And we also need to look at the speed of the motor. So still, we use this single node, node to ground. You can use this. This is a between two nodes. You have a positive and negative, but here is always detect or measure that point voltage from that point to the ground, any ground. Okay. So in this circuit, probably you want to have a ground somewhere in element. So this ground somewhere here. Okay, no worries. Okay, so now we have a complete circuit there. So detect is I'm going to change it to N as the speed N. Right. So we have a complete circuit now. Now the simulation parameters. We need to put in the simulation parameter to define how long you're going to simulate the circuit. Let's say we're going to simulate for 4 seconds, right? And you're going to start with 0, and then you want to simulate 0.0001, for example. Let's have a look. 1, 2, 3, 4. Okay, so we have 1 to the power of minus 10 to the power of minus 4, 0.001, and look at what happens to the circuit. So we're going to stop at 4, and we're going to record all the data, all the time, all the points starting from 0. You can change this actually. Print time. Print time is where you want this Psim to start record, to start save the number of points. Instead of starting from 0, probably you want to start at 3 seconds, which means you just want to look at the steady state operation. Right, then you put it. So let's have a look. This, break. Then go to run. Go to simulate, then transmission. Okay, the maximum number of data points is 1000 data. So let's have a look. Yeah, because it beyond the demo version, so I have to adjust the number of points. Don't worry. Just have a look at the speed. Look at that. Instead of 8, look at that. Start from 3 and just up to 3.6. So what does it mean? So this simulation only shows you this is the disadvantage of using the demo version. You cannot have all number of points being saved. It limits to 6,000 points to be saved by the PC. Okay, so that's why if you look at this graph, this is a speed graph. This is the speed graph, and you just only see from 3 seconds up to 3.6 seconds. So if you use a full version, you can start from 0 and it will stop at 4 seconds. But if I can change the y-axis here, change the y-axis. I don't want to be auto scale. I want to start it from 0, and then let's say this is 1,400 RPM. Let's see what happens to the graph. Look at that. Actually, it shows me that the speed of the motor is actually 1,002, but almost close to 1,200 RPM. Okay, so this is speed that you have, 1,200 RPM. What about the current? Okay, so if you look at the armature current, it gives me again. If you look at the value here, it's very close, isn't it? It's very close, 1.09. This is very small. variation. So I actually can change the y here and change it from 0 until 1.1, for example. Okay, so the current is actually, and I can change the speed again from 0 to 1400. Okay, so the current, armature current, is about 1 point something, and I also can look into the IF. IF, it is 1.6, isn't it? Because we have, again, I've shown you just now, double click that. So if you the field current, it is RF is, we have a 75 ohm, and we have the VF is also 120 volts. So 120 volt divided by 75 ohm. So that will give me IF equals to 1.6. However, the current is only 1 point, armature current 1.6. And with that voltage VT, we have 1200 RPM, so close to our 1000, just slightly above 1200 RPM. Never mind. So that is how you're going to simulate the circuit. Okay, don't worry, I'm going to share with you this video recording session, this session. So do it, slow. Try it yourself. Start from zero. Start from a blank document here. Repeat again the step that I did with you. Then try to simulate. And we know that the speed is 1200 RPM per day. Okay, with that, I show you again. Keep on changing, no worries. Change that from zero. Speed from 0, 1500. So it's close to 1250, no worries. It's still about that 1200 RPM. Okay, let's look at what happens to the summation here when you reduce the speed of the motor. Okay, we want to reduce the speed of the motor, so I'm going to reduce that VT to half of it, half of the 120 volts. So let's see, 60 volts. Here. Change that VT, and I want to modify a bit. Total time for, let's see if I can reduce the time step. This is time step between the data that you're going to save. This is known as time step, which means what it does is that PC will convert everything into the equation, differential equation, and each of the point is based on that differential equation, and it start with 0, and then it will increase. The next point will be 0.001. The time is 0.001 second. Next point will be that 0.001 plus 0.001. So this is known as a time step. How you change the t to be able for you to calculate, to solve for the differential equation of the circuit. Right? So the time step is actually determines how smooth. If you have a very small time step, which means you have a fine line, isn't it? Fine detail, we call it point that you record. If you have a large, which means, for example, you have 0.01. If you have a large time step, you calculate from 0, start from 0, and then you jump to 0.1. So you miss this information between 0 to 0.1. You miss the information in between. So therefore, your circuit, sometimes you will get a nice or a correct simulation, a correct, data that you obtain. So actually, there is a rule of thumb. Normally, you're going to have at least 10% of the, if you have a switching, if you talk about switching circuit, there's a period to your switching, isn't it? You talk about 100 kilohertz, the period is 10 microseconds, isn't it? 10 microseconds. So the time step should be 1%. It should be very small, at least 1% of the period of your switching. So which means in this case, I can put as a 0.001 instead of 0.001. I'm going to try with 0.01. Let's have a look. Okay, so run again. Run transmission control. Now let's have a look. There you are. Okay, so I can simulate that. And now, if you look at the speed, I can close up. So the speed now changed from, I have to reduce this 0 to 0. Okay, I look at the speed now. It reduced to about 6,000 plus from 1,200 RPM. And if I apply that voltage is reduced, right? So if I reduce that voltage, now the speed reduced to 6,000 RPM. And if you look at the current still maintained, if I'm not mistaken. We still have the same current, armature current. Of course, IF is at 1.6. There's constant torque, and therefore you have 600 RPM compared to 1,200 RPM. So almost half of the voltage, almost half of the speed. Okay, so that is very much the Psim circuit simulation. So make sure that you try it, right? Because later on we're going to combine with the rectifier circuit, isn't it? And also we have DC-DC converter circuit later on, yeah, by using the Psim. Okay, so that's it for today's class. I'm going to share with you afterwards the video, and please watch it. It's only about 1 hour video, and the notes is already on the drive, Google Drive, and this is the new slide which correspond to the new video that I'm going to post afterwards. Okay, so solid state control. Now we have this solid state control whereby you're going to change the VT by means of using the converter. Okay, so solid state control. So how to do it? All right. This is okay, the definition. What is a base speed? And this is a talk about the constant torque. Constant torque. And then we have also a constant power, but torque is reduced. In that power, as constant power operation, the torque is reduced, but the power is constant. Okay. And then there you are, control rectifier. So we start with and always you need to understand the 4-quadrant operation. This will determine how you're going to control your DC drive with respect to the application, with respect to the load. Right? You know, it represents a whole operation, the complete operation of a DC of a drive. Yeah, so you need to understand what is a 4-quadrant. Please refer to the YouTube channel. What's a 4-quadrant operations, and look for YouTube videos. I think India has produced a lot of videos on the electrical subject, and compared to the English, compared to the others, Western. India has a lot of the Indian. Okay, so again and again, always remember that we have omega here, torque is there, then we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. If you change the top with respect to speed, now the quadrant also change from 1, it goes to 2 here, 3 there, 4 there. Look at the arrangement. If you have omega versus torque, then you have 1, 2, 3, 4, counterclockwise. But if you have torque and omega, then you have it the clockwise direction. 1, 2, 3, 4. Okay, don't get yourself confused. And sometimes we also can represent the 4-quadrant operation with voltage or current. The armature current here and the VT or VA, sometimes known as a terminal voltage or sometimes VA, the armature voltage. And then you have 1, 2, 3, 4. Okay, so this is okay, everything in the video, right? So just a download, and also I hope you can find the book of Muhammad Rashid book, or you can have a PDF. I couldn't find the PDF file of Rashid. Okay, so you have to look for yourself. Rashid's book, Muhammad Harun Rashid. Muhammad Harun Rashid, Powertronics books. It's a Powertronic application, fundamental application of Powertronics. On the page 3, and you also have to look at the Sharkawi's Sharkawi book that also discuss in detail the derivation and everything. Okay, I think that's it. Any question from all of you? Okay. So again and again and again, if you would like to ask any question, just post on the WhatsApp group openly. Inshallah, I will try to answer using that platform, WhatsApp. Okay, so I'm going to share with you the session recordings of this session, as well as the new video for you to watch, and also some additional video from the YouTube on the simulation, or I think you will get confused with that. You just follow whatever share with you just now on how to simulate the circuit DC motor using a PC. Okay, right. So until this Friday, have a good day. Assalamualaikum warahmatullahi wabarakatuh. Thank you. See you again.
Thank you, Dr.
Thank you, Doctor.
Thank you, Prof.
Um,
Thank you, Doctor.
okay. Bye.